Hello everyone, and now I'd like to continue the discussion about bonding. What is holding the materials together, and you're going to learn the second type of bonding called covalent bonding in this section. So let's review a little bit, and as you can see on this is the periodic table. Very nicely color-coded, and you will see noble gases as the electron configuration of the noble gases are the most stable one, as indicated by the chemical stability of those elements. All the other elements on the periodic table are less stable than the noble gas elements, so they all want to move into that direction and achieve the noble gas electron configurations. Hence, it's called Octet Rule. It's Octet Rule. The group 17 elements, they tend to gain 1 electrons to get 8 because they already have 7 valence electrons. Group 1 alkaline metals, lithium to francium, they tend to lose 1 electron, valence electron, because it has 8 underneath. Much easier just to lose the 1 and achieve the 8 valence electrons. So the same token, the group 2 will lose 2 valence electrons to achieve the octet. Transition metals, much more complicated, is where the d electrons are involved. So when we have a complete gain or lose electrons, as indicated by the example, is sodium is you plus the Cl2. The Cl2 eventually is going to give you a 2Cl, and this is going to be a Cl. So the sodium atom and the chlorine atom. The chlorine atom has 7 valence electrons. The sodium has 1. It will be much easier to actually have a complete transfer of electron going from the sodium to the chlorine. So then you have sodium plus ion and chloride minus ion. And we went through this in detail in the previous podcast, talking about you have the positive charged ion and the negative charged ion, and the positive and the negative, positive. It can be packed repeatedly and form a ladder structure. This is all based on when we have this positive and the negative charged ion interactions. The interactions called ionic bonds are totally non-directional, which means it doesn't matter which direction the opposite charged particles are approaching each other, they have the same attraction. And also this macrostructure with the lattice and everything will explain nicely the bulk properties of ionic compounds. So it will be interesting actually just to take a look at some other situations. So what would happen if 2 hydrogen atoms approaching each other? As you can know, for hydrogen atom, the Lewis star structure, the valence shell electron configuration is just 1 electron. It's less stable than the noble gas element. The corresponding noble gas elements will be helium. Helium will have 2 valence electrons. So those 2 hydrogen atoms would love to achieve that. And if just go by the traditional way of forming ionic bonds, so we will say, okay, so one of the hydrogens is going to lose that valence electrons to pass on to the hydrogen atom next door. So then you're going to have hydrogen. This one's going to be negatively charged, and that one, the hydrogen atom that loses this valence electron, will be positively charged. However, this entity probably is happy because it has 2 valence electrons, but achieved the helium configuration. However, this is going to be extremely unhappy because it does not have any electron anymore. So what would be the alternatives for just grabbing these electrons? Will be for the hydrogen atoms to share this pair of valence electrons. That means that is the sharing means is actually it's being shared by this hydrogen nucleus and these the two valence electrons. Now you have a helium electron configuration. On the other hand, you also have the sharing. This pair of electrons can be onto the other hydrogen nucleus. Also achieve two valence electron, the helium electron configuration. So this is a win-win situation. Okay, so both hydrogen atoms accomplish the task of achieving helium electron configuration. And in this case, what we're going to have here is we're going to have a notation. You can have hydrogen will be linked with hydrogen through a single bar. And now you understand this single bar represents a pair of shared I emphasize the word shared valence electrons. Okay, so here now you learn the definition of covalent bond. As indicated by the name co, as in the collaborative, cooperative, it always means what? Sharing. Valent, it means the valence electrons. So this is the emphasis is on the sharing. As compared to the total transfer of valence electrons in ionic compounds. So let's take a look at some other examples. Let's take a look at some other examples of covalent bonds and how they are formed. And what you can tell is, let's take a look at if we have oxygen and the oxygen atom together. And as you recall, what we first step to do is draw the Lewis-Dot structure. Lewis-Dot structure represents the valence shell electron configurations. For oxygen, you will have, how do you draw it? Very interesting. You have to go through the process because the oxygen, you will have 2s2 for the 2p4. That's the valence shell electron configuration. 2s, 1 box, 2p, you have 3 boxes. First pair comes in here. This one has to go up first before you're coming back down. For the reason is the Hunt rule. This gives you the lowest electron configuration, called the ground state electron configuration. So what you need to know is now you have 2 pairs. This is pair and that is pair, valence electrons, and the 2 singles. Same here, 2 singles and 2 pairs. So what would be this win-win situation here is, the win-win situation here is they are going to form sharing of 4 valence electrons. The sharing of 4 valence electrons. This is the sharing of the 4 valence electrons. Sometimes we write it oxygen double bond. Remember, each bar represents a pair, 2 shared valence electrons. 2 shared valence electrons. So it would be very interesting. Same token, you're looking at for nitrogen. I like to use to draw with the blue. Now you have 3 unpaired valence electrons. Venture to take a guess what kind of bond it will form. It actually will form a triple bond. It will form a triple bond. Okay, it will form a triple bond. In this case, now you start to understand why you always have hydrogen as H2, nitrogen is N2, oxygen is O2, fluorine is F2. Oh, let's take a look at fluorine, how it actually forms. Fluorine will have 7 valence electrons. The other fluorine will also have 7 valence electrons. You will be the best. You will be just the fluorine. 1, 2, 3, 4, 5, 6, 7, 8. Share this value. 3, 4, 5, 6. And it gives you the stable structure. It will give you the stable structure. And now we actually would like to take a look at info much more detailed about valence electrons, covalent bonds. Let's bring back what we called the hydrogen, like the hydrogen atom. So what we have here now, a hydrogen molecule now, it's this hydrogen, and compare to that hydrogen. But if you look closer, so they will have, this is the hydrogen nucleus. Now we have, this also is the hydrogen nucleus, and that's the electron, the valence electron. What will be the interaction between, let's see, this and this. So the nature of the interaction is still very strong. Electrostatic, sometimes to refer to as electromagnetic attraction. Okay, so here is between positively charged nucleus and valence electrons. Okay. So hence, what we call it, the covalent bonding, the covalent bond are very strong. For the reason it still is the positive and the negative. And also, one of the very key property is, as you can see, those electrons are quite confined between the two nucleus. The most effective way, the most strongest interaction will happen when it is right in the middle. So the valence electrons are much confined, shared valence electrons are much confined, and hence covalent bonds are highly directional. Okay, meaning what? Meaning if it's a hydrogen is linked with hydrogen, it will be just confined between the two nucleus. It's going to be different if we're going to move on to this one, move on to this one. It is confined very in a very defined space between the hydrogen atoms. So now we'll actually learn covalent bond. It's pretty strong because the nature of it is still the positive interaction between the positively charged particle and a negatively charged particle. Okay. So now you start looking at it, and what is constituted a covalent bond, and what is the difference between a covalent bond and an ionic bond. So let's take a look at some other kind of what we call covalent compounds, and let's see what the features are. Okay, so then let's take a look at one particular compound. Is hydrogen chloride. So it's between hydrogen and chlorine atom. It's between hydrogen and chlorine atom. This is going to form, see, like hydrogen is 1, and the chlorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So ideally, the chlorine will grab the hydrogen, the valence electron from the hydrogen to get to 8. However, because of the negativity of those two elements are kind of fairly close, chlorine is not strong enough to pull off that feast. So what you're going to do is you're going to end up with a hydrogen is sharing the electron with chlorine. 1, 2, 3, 4, 5, 6. So that's slightly different from what we've been experiencing, because experiencing is hydrogen versus hydrogen, and the two valence electrons are shared in the middle, and it will be the oxygen will be oxygen, and the oxygen, those shared 4 valence electrons will also be sitting right in the middle. But as I draw it here, you have noticed this pair of electrons constitute this covalent bond between the hydrogen and the chlorine is actually located closer to chlorine. Why did I do that? And if you can pause and think about it, it actually makes sense. Say the chlorine has a higher attraction to the electron than compared to hydrogen. Which parameter it actually makes sense to have that? That would be the electronegativity. It's the measure. It's the measure of how strong the atom is attracting the electron. So when we have that situation, let me reproduce that. That will be a hydrogen, and you will have, in this case, it's chlorine. One, 2, 3, 4, 5, 6, and 8. So because this have extra electrons spending a little bit more time on the chlorine, so this is in part slightly negative charge, because this electron is supposed to belong to the hydrogen. It's moving away from it, so it's going to give you a slightly positive. And we use a symbol like this to draw it, to indicate this is actually have an uneven distribution of electron density. So this one has uneven distribution. And in this case, it's a shared valence electrons. Okay. So what we call here is, this is, oh, let's get rid of that. This is what we call polarity. If we have a partial charge separation, the bond is polar. The bond is polar. So as we move along, as the difference in the electronegativity increases, which means the electrons, shared valence electrons, move closer and closer to the element with higher electronegativity. So when we actually, the difference in electronegativity is strong enough, and the valence electrons actually complete those process and becoming complete ions. So actually I have some YouTube video clip I want to show you to clearly demonstrate the different bonding between the ionic and the covalent. So let's take a look at this one.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Pretty cool, huh? And this is a good demonstration for the differences of ionic and covalent. And as we can see here, and this is another link for a very good animation for all the way from the ionic compounds to the ionic compounds to the covalent compounds. And also within the covalent compounds, we're going to make a distinction between what we call it nonpolar, and that will be the no separation, primarily this no separation of charges, to polar covalent. They will be the one with separation, kind of partial separation of the charge. Okay. So what is actually going to be the cutoff between ionic bonds versus covalent bonds? So this one is actually, there's a rule of thumb, as we talked about it before, the electronegativity. The electronegativity. In this case, is actually the difference. Let's use the delta in electronegativity. It's the difference of electronegativity between the two elements that is forming the bond. It's going to be crucial. It's kind of logical to understand that, as the difference, if we don't have much of a difference between attraction to the electrons will be, shared valence electron will be sitting in the middle, as indicated by, if we say the first example will be the hydrogen gas. Okay, so the H2, you will be the H and the H. Since there's no difference between those two elements in terms of attraction to the pair of electrons that's being shared, those pair of electrons will be sitting right in the middle between the hydrogen and hydrogen. Now, the way I draw it, let's just redraw it. And this one will be, okay, the shared pair of electrons will be distributed right in the middle. So in terms of the En is 0. Okay, So now we're talking about this as nonpolar covalent. So this rule of thumb is if it's less than 0.3, we call it nonpolar covalent. It's between 0.3 and the x will be the difference. X will be this, the difference of electronegativity between 1.0, we call it slightly polar covalent. Okay, so this one will be called slightly polar covalent. Okay, so then this is one. Between 1.0 and 1.7, this one is called polar covalent. Means it actually has more and more separation of charges. And if it's greater than 1.7, if the difference is greater than 1.7, generally we'll assign it as ionic. There will be some exceptions to that, and you will learn that in a higher level class. So this is the key to identify the nature of the bond, either to be nonpolar covalent all the way up to the ionic. One thing I want you to really understand that is actually, even though we talk about different kinds of bonding, it's just to the different extent the shared electrons are being located. The valence electron will be located. It will be from right in the middle. There will be no difference, no charges, no charge separation. It's called nonpolar, but it's covalently linked. Slightly increasing the difference of electronegativity will bring you to slightly polar covalent region, and it will go, if it goes higher, it's between 1.0 and 1.7, that will be the polar covalent region. And if it's greater than 1.7, it's essentially the one element with the higher electronegativity tells the element with low electronegativity, give me the electron. So you transfer the valence electron or electrons to complete into ions. So it's ionic. So let's take a look at the other example is CS2. Later on I'm going to learn this is actually called carbon disulfide. So you're going to form a carbon and a sulfur bond. What we're going to check on is the nature of this bond, and we need to electronegativity values. You can actually call up the ptable.com and put it into the properties. If I highlight the electronegativity, if I want to check on carbon, in this case I want to see carbon is 2.55, sulfur is 2.58. So this one, it will be the delta En, the difference electronegativity, will be 2.58 minus 2.55 equals 0.03. So that is much less than 0.3, the threshold for what we call it nonpolar. So those bonds, the CS bonds, it's nonpolar covalent. Okay, nonpolar covalent. We're going to do the same thing for water, and that will be H2O, and the difference is H has the electronegativity 2.20, which is surprisingly high. O is 3.44, so the difference will be 1.24. In this case, it falls between the 1.0 and 1.7. The nature of this bond between hydrogen and the oxygen, I'll draw it here. You will be polar covalent. Okay. The last one I want to calculate is sodium bromide. It will be sodium bromide. Okay. So the delta En in this case, if you check all this value out, will be 2.06, and that has to be ionic. So now you have the ability actually to distinguish between those two types of very important bonding types. So the other thing is, let's revisit, take a closer look at the interactions. As we said before, let's reproduce the hydrogen. Let's reproduce the hydrogen. So the hydrogen has a shared pair of electrons and everybody will be happy. But if you imagine you have another hydrogen here, can it come in? And you should quickly understand the answer is no. The answer is no. Because you can make an argument, they have the overlapping of orbitals and have 2 electrons on it. The third electron cannot come in. That's what? That's Pauli exclusion principle. Okay, so now you have kind of a bunch of those hydrogens. It's a hydrogen linked with hydrogen because the other one cannot come. So the other one will be hydrogen linked with another hydrogen. This one will be hydrogen linked with this hydrogen. It's sort of a self-contained unit, and now those are forming the unit, well, we call it molecules. And in this particular case, it will be H2. It's represented by H2. Each molecule composed of 2 hydrogen atoms. And if this is 2 hydrogen atoms, and then it's linked by a covalent bond. It's linked by the covalent bond. But if we take a look at it, what is between the hydrogen atom? This is a covalent bond. Very strong. However, if you're looking at the interactions between the molecules, is much weaker. So this is much weaker. Okay, so it's very interestingly. So this is what we call it. This is called intermolecular forces. It's in between the molecules. In the next unit, you're going to learn in much detailed fashion about intermolecular forces, and for those, actually, between hydrogen atoms within the molecule, it's called intramolecular forces. Okay, this is strong due to the nature of it. You remember, electrons and the nucleus, positive and negative, and this is much weaker. Much weaker. So now you have kind of a model for the molecular compound. You have molecules, and within the molecules are very strong intramolecular forces like the bonding, covalent bonding. However, it's in between those molecules, it's called intermolecular forces, and they are actually much weaker compared to the positive and negative electrostatic interactions. So as we said before, and you've done the lab, and you start observing properties of a covalent element or compounds. In this case, you have a covalent or / molecular compounds. It will be the table sugar. It will be the sugar. Okay, and usually they are dull in appearance, and they're soft and brittle, fairly low in melting and the boiling temperatures. Actually, at room temperature, lots of those molecular, either be the elements or the compounds, are gases, like in hydrogens, oxygens, nitrogens, chlorines. those molecular or covalent compounds or elements, they do not conduct electricity. If you melt it, it doesn't matter. It doesn't conduct electricity. And some of them are actually readily soluble in water. Case in point, that would be the table salt. That will be the table sugar. Okay, and you also tested the aqueous solutions of the table sugar. It actually turns out does not conduct electricity at all. It does not conduct electricity at all. But however, you do see the table sugar disappear into the water. So how you account to all those? And here comes, as we said, the microstructure. Let's take a look at what. Let's bring out the blue color. So for all of them, like in the hydrogen, we have all this. It's kind of graphically represented here. Those are molecules. And remember, those molecules do not have really separated charges. So this is the one and versus the complete. Okay, so this is the ionic, this is the covalent, this is the covalent, or sometimes referred to as molecular, okay, so this is the ionic. So you will see the structure, the microstructure, quite different, and this is the exact reason why covalent or ionic compound behave like what they behave. So what are the explanations? What's the correlation between the bulk properties, observable properties, and the microstructure? As we draw it over there, it becomes molecules. And as you can see here, it is very strong interactions between those, strong interactions. And in between here, much weaker. Okay, here it's much weaker. So why they kind of also like in ionic compound, they're dull in appearance? Because they do not have free electrons. Why they're soft and brittle? Because the intermolecular forces between those molecules weak, much less, okay, much stronger. Actually, much less strong. Okay, and why it's low in melting and boiling temperatures? Same explanation, because the interaction between those molecules much weaker. It do not conduct electricity in either solid or molten form. They do not have ions. They do not have any charge carriers. Some are readily soluble in water. Later on in next unit you will learn some of them are very soluble in water, some of them are not, and going to recall the rule of like dissolves like, but that's not going to be covered in this unit. But when they dissolve in water, you see them all disappear. They will be carried away by the water molecule. However, we do not have any charged particles. Again, they have individual molecules. Hence, the aqueous solutions of covalent or molecular compounds is non-conductive. But everything has some exceptions. Case in point here is the diamond. If you're looking, everybody knows the fact, right? The diamond is the hardest material on Earth, hardest of materials on Earth. And then you have to take a look at the diamond is composed of pure carbon. pure carbon. And as you can see here, this is a single crystal. Okay, those are single crystal. What it has here is, you see those balls representing the carbon atom. They all covalent bonded to another carbon atom. So as a whole single crystal, they all bonded covalently for the carbon atom. As we know, the covalent bond is very, very, very strong, because it's still the nature of the positive charged nucleus and the negatively charged valence electron. They interact. So this whole single crystal is a total network of this tetrahedrally bonded carbon. So as a result, as we know, the covalent bonds are very strong. So that's the reason why the diamonds are the hardest material on Earth. It's just so hard to rip the carbon atoms out. However, if we compare to another element that's made of carbon, it's graphite. And you have layers, and each layer is very, very strong and very, very stable. However, in between those layers, those interactions are weak. So hence those layers, and in between here very strong, within the layer is very strong, but in between is much weaker. So actually we use it in a pencil. The one left marks on the paper is actually you leave some of the graphite behind. It's because within each sheet very strong covalent bonding between carbons. However, it's in between those sheets that kind of doomed the graphite's strength in terms of mechanical properties. So you can easily guide against each other. So just to simply wrap up, here in this vocast you learned about the covalent bond, covalent elements or molecules, and how to distinguish between ionic bond and covalent bond. And within the covalent bond you can range all the way from a non-polar covalent, which means they do not have a separation of charge, to all the way to polar covalent, because they do still link covalently, however they have uneven distribution of valence electrons due to the differences in electronegativity. And from there you can know the microstructure of the molecular compound. Actually, that details of the microstructure dictates the property of molecular compounds or the elements. As we said before, the intermolecular forces are much weaker compared to the intramolecular forces, and those are the bondings. And the property is soft, brittle, low melting point, low boiling point, all comes into play. With that, you should consult the worksheet for exercises. And thank you very much for your attention.